This video is about Newton's second law. In the last video we learned about Newton's first law, which said that the net force causes changes in motion. The second law says, not surprisingly, that the larger the force is, the greater the acceleration will be. Because remember that acceleration tells you about the way velocity is changing. And the equation is F net equals ma. F net and a are both vectors. M is the mass. It's a scalar. It does not have direction. And so that means you have a vector multiplied by a scalar gives you another vector, and the two vectors have to point in the same direction. What mass is sometimes also called inertia, and it's the degree to which an object resists changes in its motion. So something with a large mass needs a large force to get a certain acceleration. Mass and weight are not the same thing. That's another thing you should remember from last year. But they are proportional in a particular gravitational field. And because F net and A have to point in the same direction to be equal, what that means is that if acceleration points in the x direction, what that tells you is that the x component of the net force equals ma, and the y component of the net force equals 0, which is quite useful because this is essentially two different equations. And that means we can solve a lot more problems with two equations than with one. So here's an example. We've got a 720 Newton crate. It slides across a frictionless floor. You're pushing it with a force of 92 newtons that is angled 20 degrees below the horizontal. What you want to do is find the acceleration of the crate and the magnitude of the normal force from the floor. So first step is draw a picture, free body diagram. We've got a crate sitting on the floor. It's going to have its weight, and we know that its weight is 720 newtons. And we have also a normal force from the floor. And we have the force that you are exerting on it. It's 92 newtons. And it's 20 degrees below the horizontal. And there's no friction. So looking at this, at the situation, you can tell that the acceleration of the crate is going to be along the direction of the floor. Don't put the acceleration on your free body diagram because it's not a force, but it's a good idea to know what direction it is. And so we'll make those our x and y coordinates. And to find the acceleration, we're going to be looking mainly at the x coordinates because that's the direction of the acceleration. And so we know that F net x equals ma. Now if we look at those forces, only one of them has an x component that is not 0, and that's the force that you exert. So that component is going to be 92 newtons times the cosine of 20 degrees, and that's equal to the mass of the crate times its acceleration. But we don't know the mass of the crate. However, it's easy enough to find out. Remember, mg equals the weight, where g is the gravitational field, 9.8 newtons per kilogram. And so m equals the weight, 720 newtons, divided by 9.8 newtons per kilogram. And we find that the mass is 73.5 kilograms. And the acceleration then is going to equal 92 newtons times the cosine of 20 degrees divided by 73.5 kilograms. And we get 1.18 meters per second squared for part A. Now for part B, what we're going to do is we're going to say, oh, well the normal force points in the y direction, and I know since the acceleration is in the x direction, I can say F net y is equal to 0, and use that to find m. And so I ask, okay, what are the y components of all the forces? Well, the weight force is easy. The weight force's y component is negative 720 newtons. The component of the force that you exert that points downward is 92 sine 20 degrees, and that's also negative because it's pointing downward-ish. And the y component of the normal force is just n. It points upward, so it's positive. Add those all together, you get 0. And put it in your calculator. You find that it is equal to 751 newtons. It's a relatively easy example, but it shows you how Newton's second law works and how we use it. Here's another example. You've got a 6.0, I believe that's kilogram, box slides down a ramp angled 35 degrees to the horizontal. Magnitude of the friction force is 3.5 newtons. Find the box's acceleration and the magnitude of the normal force. Draw a picture. There we go. Free body diagram. We've got the weight of the block. We've got the normal force. We've got the friction force, 3.5 newtons. And we want to find the block's acceleration. Now we should be able to guess at this point that it is the acceleration points down the ramp. Incidentally, we'll also use a coordinate system aligned with the ramp. And we will say that because the acceleration points down the ramp, the x component of the net force equals ma. And then we ask, which of these forces have an x component? Well, clearly, the friction force has an x component, and its x component is negative 3.5 newtons. The normal force does not have an x component, so we can ignore it for now. And that's good because we don't know what it is. And then the gravitational force has an x component. Remember, when we are finding components of vectors, we draw right triangles. And its x component is opposite the 35-degree angle. So we have the weight force, which is 6 kilograms times 9.8 meters per second squared, times the sine of 35 degrees, and all that equals ma, 6 kilograms times a. We can do a little bit of math and algebra, and we have 6 times 9.8 times sine 35. And we find that the acceleration is 5.0 meters per second squared. Now the normal force, I'm going to let you do that. Remember, because it points in the y direction, you're going to be using F net y equals 0. And it happens to be identical to the problem we worked in the last video where it was not sliding. Remember, the y direction, there's no acceleration, so there's really no mathematical difference from the earlier problem. Last topic is elevator problems. You've noticed that sometimes you feel heavier in an elevator than you do just standing there. And that is when it begins to start going upward, and when, if you're moving downward, when it stops moving down. And then you feel lighter when it stops moving upward, and also when it starts moving down. What these have in common is that in both of these cases, the acceleration is upward, and in the cases where you feel lighter, the acceleration is downward. Now what we need to establish, though, is a free body diagram. When you're in an elevator, there's your weight that acts on you, gravity, and there's also a normal force from the floor. And those are the only two forces. Gravity does not change. Your weight is the same. We're assuming that you're not in the elevator long enough to lose an appreciable amount of weight. And so if you start accelerating upward, it's because the normal force is larger. So normal force here is larger than your weight. And if you're accelerating downward, it means the normal force is smaller than your weight. And what you feel is the normal force. Let's say the floor goes away. I don't know if any of you have been in free fall before, but if you've been in free fall, you know that you feel weightless because you're not feeling any normal force up from the floor. And so when the normal force is less and you're accelerating downward, you feel lighter. And when the normal force is larger than your weight, you feel heavier and you accelerate upward. Now for tomorrow, I'm going to check question 5 from chapter